Before explaining Newton's second law, let's review the key concept of Newton's first law. If the net force is zero, an object at rest remains at rest, and a moving object continues its motion with a constant velocity. Now consider this track. The toy track rests on the ground under the action of two forces, the weight exerted by the earth and the normal force exerted by the ground. The sum of these forces is zero. The toy track tends to stay at rest. It will stay at rest as long as the resultant force acting on it remains zero. Now the toy track is moving with a constant velocity under the action of four forces: the weight, the normal force, the friction, and the driving or the traction force. The toy track tends to stay in uniform rectilinear motion. It will stay in uniform rectilinear motion or moving with a constant velocity as long as the resultant force acting on it remains zero.
What happens if the net force acting on an object is different from zero? Look at this crocodile animation. This car is acted upon by four forces. The weight of the car cancels its normal reactions since these two forces equal in magnitude but opposite in direction. The driving force or the traction force has a magnitude greater than that of the friction, and these two forces have opposite directions. So the net force acting on this car is different from zero. Then this car moves in an accelerated motion. So Newton's second law states that the acceleration of a moving object is directly proportional to the resultant or to the net force acting on it and inversely proportional to its mass, so that sigma F external, or the sum of the external forces, is given by the mass of the object times its acceleration.